Bismillahirrahmanirrahim. Assalamu alaikum. In this video here today, we are going to talk about a device called a cathode ray oscilloscope. A cathode ray oscilloscope is a device that is used for basically plotting graphs. It is a device for plotting graphs. An oscilloscope will always plot a graph of voltage on the y-axis and time on the x-axis. Where does this voltage come from? It's actually an electrical signal which may be generated um, by a sensor. In our syllabus, we only have to deal with the time-based settings and the Y gain settings. We only have to deal with that. But I'll give you a little insight as to how the CRO works. Keep this in mind. We don't have to know how the CRO works or what is the structure of CRO. It's not relevant in our syllabus, but to understand what is time-based setting and what is Y gain setting, you would have to actually understand the working of it. They will not ask you to actually describe it, or they will not ask any questions from the structure, but it will be easier for you to understand these two terminologies if you understand the structure of a CRO. This is what a CRO looks like. A CRO is going to have three major parts. First is an electron gun. Electron gun has many parts. I'll show you. Okay. First of all, this little spring-like structure that I have drawn, this is a heater. This is a filament heater. And this little piece that I have drawn, it's a metal plate. So an electric heater is used to heat up the metal plate. When the metal plate is heated, thermionic emission takes place. I'm going to write that down for you. When heater heats up the metal, thermionic emission takes place. Thermionic emission. Thermionic emission is a process in which a heated surface gives out electrons. I'll just underline that and write heated metal surface gives out electrons. It is a process that takes place when you heat up a metal surface. Electrons are free inside a metal. So when they absorb energy, they get excited and they're bound to come out of the metal surface. So this metal plate kind of gives out electrons in all possible directions as a form of a shower. Okay, then there is this little blockage that does not allow the electrons to move forwards as a shower. There is a little hole over here. So the electrons will only be able to move through this hole. Now, after that, we have this cylindrical structure. I have shown a little cross section of it. It's like a tunnel, basically. There is a hole inside it. This structure is called an accelerating anode. This is an anode. Anode means it is attached to the positive terminal of the battery. So the electrons which were emitted here by the metal surface, the anode will actually pull the electrons outwards, giving them a horizontal velocity. Actually, there are three anodes, one after the other. Every one, the one that is after the previous one, has a higher voltage, has a higher potential attached to it. So electrons basically keep on getting attracted towards the right hand side and they don't get stuck to the previous anode. That means, for example, here, if there is the single anode that I've shown, there will be another one present outside ahead of that. And this one would be attached to a greater voltage. So electrons will not just get stuck to the previous anode. They will just be attracted forwards instead of getting stuck with the cylindrical structure. Then I'm going to draw using different colors now. We have two horizontal metal plates, and these horizontal metal plates, they are called the Y plates or the Y deflecting plates. The Y plates are going to have a voltage on them. That voltage is going to come from a sensor, PD from a sensor, potential difference or voltage from a sensor. So the electron beam that has that has been attracted forwards towards the right hand side, the Y deflecting plates are going to cause that electron beam to get deflected either upwards or downwards, depending on which of these metal plates are positive. Let's say if the bottom plate is positively charged, that means the electrons which are negatively charged, they will experience a downward force. So electron beam, instead of going straight, it's going to get deflected in the downwards direction. If the upper plate is positive, the electron beam will get deflected vertically upwards. So basically, the Y plates are supposed to deflect the electron beam vertically up or down. Then we have another set of deflecting plates. I'm still drawing that with the red. That means both of them are deflecting plates. These are vertically placed. They are called the X plates. That means these are responsible for causing electron beams to get deflected towards the right or towards the left. X plates are internally controlled. Internally controlled. That means we don't have to change any voltage on the X plates. The CRO have a little generator inside it. That generator will apply voltages on the X plates themselves. Okay, and then this part here, this is the fluorescent screen. When electrons fall on it, when electrons fall on the fluorescent screen, those electrons, they will, the spot where they fall on the screen, that spot is going to glow. So basically, if you simply look at the screen without any of the plates, you will see that okay, just a minute, it'll take me some time to draw it. This is what the screen looks like. The screen already has a grid made on it. When electrons fall on the screen, they will always fall at the center. But if the top vertical deflecting plate, the Y plate, if the top plate is positively charged instead of the bottom one, the electrons which were falling at the center, they are going to move in the vertical direction upwards. Let's say till here. If the Y plate is, it has an even bigger charge on it, the spot will move even further vertically upwards. If the Y deflecting plates, they have opposite charges. Now the bottom plate is positive and the top plate is negative. What's going to happen? Of course, the electron beam is going to get deflected in the downwards direction. So the electron beam, instead of moving upwards, it's going to start coming downwards. So the spot on the screen is going to, it's going to appear as if it is moving downwards. The X deflecting plates, these ones, the ones that I have drawn vertical, they are responsible for causing the electron beam to deflect towards the right or deflect towards the left. Okay, so as a combination, when we use the Y and X, both deflecting plates, the electron beams can also move vertically up as well as towards the right or left. That's how a CRO will work. Take a little break and see everything is okay so far or not.
Sir, how would they move left to right?
Okay.
No, why would they move left to right?
Okay, if you look at the screen from here, you would see that there are two vertical metal plates, and this is where the electrons are coming out of the page. Can you visualize it?
Yes.
Okay. So these are the vertical plates. They have a voltage which is internally supplied by the device. Internally supplied means that we don't have to attach anything on these terminals. Unlike the Y plates, we have to attach something, a sensor on the Y plates. But on the X plates, there is a little generator inside the device itself that provides voltages to the X deflecting plates. So the electron beam that is coming in between them, if this plate becomes positively charged, the electron beam will move towards the positive plate. That's how there will be a leftwards deflection. If the rightwards plate is positive, this one is positive, and this one is negative instead of positive, that electron beam will be seen to deflect towards the right. So on the screen, it's going to fall a little towards the right of the central point. Do you get that?
Sir, what if they're both negative, the plates?
Sorry, come again.
What if both of the plates were negative then? What
What
would
if
happen to
both,
the
okay, what would happen to the plates if both of them are negative? You would have to comment on which of them have more negative on it. Let's say if this one has 5 negative charges on it and this one has a lot more than the left one, so the electron beam will experience greater repulsion from the right hand plate. So that way this electron beam will get deflected towards the left. If both the plates have equal negative charge on it, electron beam is not going to go anywhere. It's just going to go straight through the center without any deflection. Do you get
All
it?
right, so sir, can the electron move up and down too?
Similarly, electrons can move up and down, but not because of these plates. They are moving up and down because of these plates, horizontal ones, which we call the Y deflecting plates. So when the electron beam is at the center, if the top plate becomes positive and the bottom becomes negative, this electron beam will move upwards. Do you get that?
Sir, do all of these plates work at the same time?
Yes, that's what I'm saying. If both the plates are switched on together, the electron beam can move towards the right or left as well as top and bottom of the screen.
How would it
I'll
move?
give you an example. Let's say right now the top Y plate is positive and the bottom plate is negative, and the rightwards plate is positive and the leftwards plate is negative. Can you understand that now the electron beam will move vertically upwards and also towards the right? So basically this electron beam would appear somewhere here.
Oh, okay, okay.
So instead of the center, electron beam will appear over here.
Okay. Sir, what if all the plates were positive then?
What if they are not, if they have equal positive charges, the electron beam will not move anywhere. It will stay at the center. That's not going to be useful at all.
And the same would apply if all the plates were negative.
Absolutely.
Okay. Could you write that down, please?
If all the plates have equal charge, positive or negative, electron beam does not deflect at all. Is that okay?
Yes.
All right. Now I'm going to discuss the two important things, and that's about all that we need to know from the topic of CRO, the Y gain setting and the time-based settings. These are the two things that we only need to know. In our syllabus, it's also written comprehension of time-based setting and the Y gain setting of a CRO. Everything that I told you here, the working was just to explain these two things, all right? So I'm going to define for you the Y gain setting. Y gain setting basically means amount of voltage, amount of potential difference applied to the Y plates to provide 1 unit division vertical deflection. If you look at a CRO, there will be a lot of controls. There will be a little screen like this on which the waves will be displayed. There will be a lot of buttons and controls on a modern CRO. But basically, what is important is there is going to be a little knob over here and a little knob over here. And this is an input terminal. You don't really have to know what is happening here. One knob will control the Y gain. That means you can control how much voltage needs to be supplied on the Y plates to cause 1 unit division vertical deflection. For example, if I set the Y gain setting to be 10 volts per centimeter, that means on the screen, if this electron has to deflect 1 centimeter vertically up or down, the Y plates will have 10 volts on it. 10 volts supplied to the Y plates. If I choose this to be the Y base setting, that means when 10 volts will be provided to the Y plates, that's when the electron beam will deflect 1 centimeter vertically upwards. If instead of 10, I choose it to be 20 volts per centimeter, that means when I choose this setting, 20 volts per centimeter, electron beam will move 1 centimeter upwards only when 20 volts are attached to the Y plates. That means Y gain setting is like a control, a scale. Like when we draw a graph in mathematics or a graph in physics, we first have to decide a scale, right? 1 centimeter to represent how much of a value. Similarly, Y gain is like deciding a scale. That means this will show us that how much voltage will be supplied in the Y plates to cause 1 centimeter vertically upwards deflection. Do you understand that?
Yeah, I got it.
Okay, that's great. So if I tell you that 20 volts per centimeter is the Y gain setting, and on the diagram I show you that this is where the electron beam is. This is the central line. Electron beam has deflected 2 boxes vertically upwards. Now we already know that the Y gain setting is 20 volts per centimeter or per division. Here the beam has deflected 2 centimeters upwards. That means somehow on the Y plates there was 40 volts attached to it. That is why the electron beam deflected 2 boxes. I'll show you like a formula here. Voltage supplied equals to number of boxes deflected multiplied with Y gain setting. So the case that I just discussed, Y gain is 20 volts per centimeter. And how many boxes were deflected upwards? 2 centimeter, or 2 boxes were deflected upwards. So the centimeter gets cancelled out with centimeter. So it turns out that the voltage supplied is going to be 40 volts. This is what you are expected to know how to calculate. Do you
Sir,
understand
could you
that?
explain the working again?
Y gain setting will be given in the question. Just by looking at the diagram, you would have to see how many boxes the electron beam has deflected upwards, or in some cases downwards as well.
So, sir,
Just
one box is 20.
Yes, one box, because the setting was 20 volts per centimeter. So one box deflection would represent a voltage of 20. So if the electron beam deflected two boxes, that would mean 20 plus 20. So it comes out to be 40.
So 40. Okay. Sir, what about the units thingy? Could you scroll down, please?
Okay. The Y gain setting has a unit of volts per centimeter.
Okay, okay. So you did the units with this values. Okay.
Yes, with the values only. Okay.
Okay.
All right. If in some cases voltage supplied is given and they ask you to find out the Y gain, what's going to happen? Voltage supplied will be divided with the number of boxes just to find out the Y gain setting. Okay, once more, if they have given you the supplied voltage, let's say I tell you I have given you 80 volts and there were two boxes deflection. That means one boxes would represent a deflection of a voltage of 80 divided by 2.
40.
Okay. So if there were, if the beam was deflected two boxes upwards and it was given in the question that total voltage was 80 and they ask you to find out the Y gain setting, that is how you'll be able to find it out. Simply,
Okay, sir, what if the boxes were deflected down? So would that give us a value in negative?
yes, that would tell us that how much voltage was given to the bottom plate. If the electron beam was deflected downwards, that would mean the bottom plate was positive instead of the top plate. Okay. That would just
Okay.
mean that the electron beam got deflected downwards because the bottom plate was more positive than the top one. That way we would still be, if you want to find out the voltage from the bottom deflection, the process is still going to remain the same. If there was one box deflection downwards, that would mean you multiply Y gain setting with one box. If there was two boxes vertically downwards deflection, you'll multiply the Y gain with two boxes. Same process.
Okay.
All right.
So it wouldn't give us a value in negative because the plate is positive.
Yes.
Okay.
Okay, now I'm going to tell you about the time base settings. The time base actually means time taken by electron beam to get deflected one division horizontally. Now, what does that mean? That means, imagine that's the screen again. And that's the graph, that's the grid that is made on the screen. Electrons were depositing at the center, so there was this bright spot at the center. When I will switch on the X plates in this diagram, the ones that are shown as vertical over here, when we switch it on, the electron beam will start to deflect towards the right or towards the left, depending on which plate is positive. So the electron beam is going to get deflected towards the right. Time-based setting simply means what will be the time taken for the beam to switch its position from position 1 to position 2. That means one box, how much time is taken for the electron spot to move from 1 point to 1 centimeter towards right or left. So basically time-based setting, the name suggests that it is going to give us time. How much time is taken by the electron beam to move 1 centimeter towards the right or towards the left. It doesn't matter. Horizontally, switching horizontally is more important. Okay, let's say if they tell you 3 microseconds per centimeter, that would simply mean that it took the electron beam to move 1 centimeter towards the right, the time that it took was 3 microseconds. Or if the spot was moving towards left, that would mean it took 3 microseconds for the spot to shift 1 centimeters towards the left. So basically, time-based setting gives us a value of time. What if I say that the electron beams deflected to 2 boxes? What was the time taken? So one box will show us a value of 3 microseconds. The other one will also show us a value of 3 microseconds. So a total time for this complete deflection will be 6 microseconds. So here I will write it as time equals to number of boxes multiplied with the time base settings. The time-based settings can also be adjusted from this second knob over here. There are different values written on the scale. You can simply switch from one setting to another, but we don't have to actually do it because you won't be needed to do this in paper 3. CRO will not be expected. You just need to know that there are two knobs that can change the Y settings or the X base setting, time-based settings. Okay, do we get that?
Yes.
All right, that's great. Now I'll show you what kind of a question you can expect from this topic.
Sir, will they give us the time-based settings?
Yes, they will give you a time-based setting, or they will give you a time and ask you to find out the time-based setting. For example, I'll show you. This is a question that will be, this is a diagram that will be given in the question. All right. They show us that's the graph that is given in the question paper. They will first ask you to find out, they have given you the Y gain in the question. Let's say that is 5 volts per centimeter. They have given you the time period of wave, that is, let's say 12 microseconds. They first of all ask you to find out the peak voltage. Peak voltage. Now, what do we have to do? First of all, locate the central line. This is going to be the central line because the number of boxes that lie above this line and the number of boxes that lie below this line, they're supposed to be equal. We can say that, we can see that the wave deflects 2 boxes above the central line or the 2 boxes below the central line. It doesn't matter which one you'd like to use for finding out the answer. For peak voltage, we should remember voltage or peak voltage is equal to number of boxes multiplied with the Y gain. So from the central line, how many boxes deflected vertically upwards? 2. The Y gain given in the question is 5 volt per centimeter. Centimeter cancels out, this gives us 10 volts. That means if 10 volts were supplied on the Y deflecting plates, they will get deflected 2 boxes vertically upwards or vertically downwards. Both of these can be used to deduce the answer. Do you understand that?
I got it.
Second, they ask you to find out the time base setting. They ask you to find out the time-based setting. Now, this might be a little tricky, but it's not really difficult. It's easy. You see, this is where I'll use a different color. This is where the wave starts from. This is where half a wave ends, and this is where one complete wave ends. One complete crest and one complete trough, that represents one complete wavelength. Just look at it, how many boxes the wave is spanning over. 1, 2, 3, and 4. One wave is formed in 4 boxes. You don't have to count where the next crest starts. You just have to locate where the first crest starts and the adjacent trough ends. From here, the time-based setting, it gives us, we need to find out the time-based setting. So we just recall the formula, which is not really needed. The time period is equal to number of boxes, now this time horizontally, multiplied with the time base settings. The time period was given in the question, that was 12 microseconds. That means these 4 boxes here will be representing this much time, because time period of the wave is the time in which one complete wave is formed. So we look at it, it's given in the question that 12 microseconds is the time period. And from the diagram, we see that the wave is spanning over 4 boxes. So time period is 12 microseconds and the number of boxes is 4. You have to find out the time base setting. Let's call that to be X. Okay, we're just calling it X just as a variable. 4 goes on to the other side. 4 was supposed to be in centimeters. So this 4 centimeter goes on the other side, becomes 12 microseconds divided by 4 centimeters. That gives us X. The answer comes out to be 3 microseconds per centimeter. That means every box horizontally is representing a value of 3 microseconds. Do you understand that?
I got it.
Okay, that's great. Number 3, they can ask you to find out the frequency. For frequency, you should remember frequency equals to 1 over the time period. In this case, the time period was given because I was trying to show you how to find out the time-based setting. But usually the time-based setting is given and they ask you to find out the time period. We will be doing that by using this formula. So once you have the time period, you just divide 1 by the value of time period, not the time-based setting, the time period. Time period was 12 microseconds. Now, if you would just take out your calculator and solve this, micro means 10 raised to power minus 6. You would have to memorize that. And that's going to give you the frequency of the wave that was displayed on the CRO. So a CRO is useful when we are trying to find out the time periods or frequencies of the waves. Do you understand that?
Yes.
That's how you are going to deal with time base and Y gain settings.
Sir, we'll have to write the answer in standard form, right?
You can or you may not, but it is preferred that you write your answer in standard form. I'm saying that you can write your answer in standard form or you may try to avoid it, but what is preferred is the standard form. That's what you should, make yourself used to of. Trying to read and write the answers in standard forms. But even if it's not there, they're not going to deduct your marks. All right, so that was CRO for you. I'll give you a question over here, okay? Another example question. They ask you to find out what is the time taken for electron beam to move across the screen. The time base setting is given. Time base is given 5 microseconds per centimeter, and on a screen they have given to you the number of boxes there are horizontally. Okay, they're asking what will be the time taken by an electron beam to move from all the way from the left hand side of the screen towards the right hand side of the screen? I will be able to find that out.
Sir, could you show the formula again?
You don't really need the formula for that. Formula is for newbies. You are studying physics for very long. One box represents 5 microseconds. How many boxes are there horizontally?
1, 2, 3, 4, 20.
Absolutely. There are 4 boxes horizontally towards the right. The formula was number of boxes multiplied by the time base was equal to the time. The number of boxes were 4. The time base setting was 5 microseconds. So when you multiply it, you get 20 microseconds. So basically that's the amount of time this little spot is going to take from moving from the left hand side to the right hand side of the screen.
Sir, what about the centimeter? What happens to that?
Each box on the screen, this one or this one, that is 1 centimeter in length. Okay? The centimeter here gets
Okay.
cancelled out with the centimeter here.
Okay, that's centimeter.
Yep.
I thought it was the other one.
No, that's
All right then.
okay. So that was CRO for you. When you will try out a few questions from CRO, I hope you do. That's when you will see that the questions, they are pretty similar to what I told you over here, but it may be slightly difficult to read it from the diagram because the waves may not actually be ending on the interval indicated. Maybe a wave ends at the center of 2 boxes. So that will be a complication that you would have to deal with. If a wave ends at a center, there will be an uncertainty. You won't be able to tell if it is exactly the center or not. So you would have to actually locate where a wave is ending exactly on a marked interval on the screen. I'll show you an example here. Okay. Now, this is the kind of wave that I'm talking about. You see that it starts from a marked interval. The half of the wave ends somewhat over here. We don't really know if it is half or slightly more than that. We can't just estimate this wave. You see, the wave ends about here. That is still not on a marked interval. You wouldn't know what value or how many boxes should you count this box to be. You will just see that this is a single complete wave and this is half a wave. So you would see that 1.5 waves, they are forming in how many boxes? 1, 2, 3, and 4. So 1.5 wave are forming in 4 boxes. One complete wave will be forming in how many boxes? All you have to do is just cross multiply it. 1.5 lambda into x will be equal to 4 boxes into 1 lambda. Lambda cancels out. X comes out to be 4 divided by 1.5. So this tells you that one complete box is going to end in 4 divided by 1.5 boxes. So this is a common mathematical complication that you would have to deal with in your papers. But the wave will not actually be ending on the exact edge of the box. So you would have to calculate by using a wave that actually ends on the end of a marked interval. Okay, so that's how you're going to deal with it. Bismillahirrahmanirrahim. Assalamu alaikum. In this video here, we are going to discuss our unit 8. We're going to start discussing our unit 8, and that is superposition. Now, this will be kind of an advanced topic for us. It's not really difficult, but students find it to be quite difficult, all right? So this is like a disclaimer for you. Superposition. In superposition, first thing that we need to discuss is going to be the superposition principle. Superposition principle. For 2 marks. When two waves transverse or longitudinal, that means this phenomena can be observed for both the types of waves, transverse or longitudinal. Meet at a point. Their amplitudes get added. Instead of amplitudes, I'm going to improve my definition a little. Their displacements get added. Okay, now imagine that I have a rope like this. All right, we have a source over here, and that source vibrates up and down. So when it vibrates upwards, the particles closest to the source, they will get deflected upwards. And when it comes down, the particles are also going to come down. That way, there will be a crest that there will be a crest that is formed, which will move away from the source towards the right. What actually happened was there were particles on this side of the crest, they will be moving upwards, and the particles on this side of the crest, they will be moving downwards. That's how this crest will appear to move towards the right. So every particle on the string is going to also try to move upwards and then come downwards because of the crest when it flows through or when it moves through this rope. Similarly, if I have another source over here, because superposition always takes place on at least two waves, there can be more than two as well, but at least two waves can cause superposition. Superposition in common words just means addition. There are other quantities which get superpositioned as well or superposed as well, like forces. When you add up forces, forces can add up to become a larger value of force. That will be called the superposition of forces. Imagine there is another source, it is moving up and down as well. This time, this source is creating a crest which is moving towards the left. All the particles on this crest, on the left-hand side of the peak, they will be moving upwards like this. And the particles on the right-hand side of the peak, they'll be moving downwards. That way, this crest will appear to move towards the left. The crest will move towards the left. More and more particles will follow the same pattern. Okay. Now, eventually, both these crests are going to meet at the center. Okay, this one's moving towards right and this one's moving towards the left. Now look at this point. Let me call this point to be P. Both the crests, they are acting to try to move this particle in the upwards direction. See, the leftwards crest will also push it upwards as well as the rightwards crest. It will also push it upwards. As a result of that, now two crests are trying to push the point P in the upwards direction. So as a result of that, this point P will get deflected upwards, but both the displacements of the waves, they will get added together. That means when the crest, leftwards crest and the rightwards crest, they overlap onto each other, the particles are going to get displaced to a resultant displacement that will be greater than the either of them. That means, let's say if this particle, this crest had an amplitude of 2 centimeter, and this one also had an amplitude of 2 centimeter. So when the central points of the crest, that means the peaks, they will meet at the same point at the center. The point P is going to get displaced to a total value of 4 centimeter vertically upwards.
Okay.
Okay, so that's basically the superposition. When they move in such a way that two waves, they act to move the particle in the same direction, the resultant amplitude gets added to give you a bigger amplitude of a wave. So I'll show you. This is what the resultant is going to look like. Resultant will have a 4 centimeter deflection vertically upwards. Such meeting of the waves is called constructive interference. That means when two waves meet so that their amplitudes get added, interference, their
So, sir,
amplitudes get added to give you a larger amplitude. Such meeting of two waves is called constructive interference. Yes, go ahead.
so one wave, no, one crest was moving on the left side and the other one was moving on the right side. So the new crest would move upwards.
It will just appear to be vertically displaced upwards. Otherwise, when both the crests will pass each other, they will again become two different crests. Only when they meet at the single point, that's when the particle will get deflected upwards or downwards. Okay, it's not going to stay there or start moving as a single crest in any direction. It will just momentarily meet where point P will get deflected upwards to a total amplitude of 4. After that time has passed, both the waves will become independent and they will continue to move in their respective directions.
Okay, okay.
Okay.
So it's temporary, basically.
Yes, it's actually instantaneous. After that instant has passed, there will be no sign of an addition of the waves.
All right, all right.
Okay, so this was constructive interference for you. I'll define it for you. It says when two waves meet to give an enhanced amplitude, that will be called the constructive interference. And the opposite for that is destructive interference. When two waves meet to give, what should be the opposite for enhanced? To give a cancelled out amplitude.
I think there's a better word that could be used.
Yes, yes, it's just not ringing any bells right now.
Yeah, exactly.
If I recall it, I'll replace it. All right. Now this would be slightly opposite to that. Destructive interference takes place when a crest meets a trough.
Yes, sir. One more question.
Yes.
Superposition is between waves, but the first example that you showed me is between crests.
So basically, a crest is half a wave, right?
So it applies to half a wave as well.
Yes, absolutely.
All right, but what about a full wave?
Okay, we'll show you that as the chapter progresses. Right now, do you understand for crests?
All right.
Okay.
Yeah, I understood the one for crests.
All right. That's where we end our lesson for today. And we will discuss this. We'll continue this in the next lesson. Okay.
Okay.
All right. I hope you
You know,
understood
technically,
everything today.